A common trap in hardware design is reaching for the microcontroller you already know. You default to the chip from your college labs or weekend hobby projects because the setup is comfortable. That comfort is a liability. It leads to rapid breadboard prototypes that look successful, followed by disastrous production runs. Wearable batteries drain in hours, and controllers randomly reset. Professional embedded engineering requires matching the silicon architecture to the physical constraints of the product. Brand loyalty has no place on a production schematic. To make the right choice, we need to evaluate the 4 major architectures dominating the industry right now: the STM32, ESP32, Nordic NRF, and the RP2040. This quadrant chart maps the landscape of modern MCUs. On the vertical axis, we plot raw computational versatility and industrial control. On the horizontal axis, we measure built-in wireless integration. The STM32 family dominates the top left. It offers massive computational power and deep peripheral control, but relies on external chips for wireless communication. The ESP32 sits in the top right, packing both high compute speeds and extremely dense wireless integration into a single package. Nordic NRF parts land on the middle right, highly specialized for wireless communication with moderate compute needs. Finally, the RP2040 sits in the bottom left, offering low-cost peripheral flexibility but zero onboard radios. Forcing a chip into the wrong quadrant for your project guarantees expensive PCB redesigns and broken power budgets later in the development cycle. Let's look inside the silicon to see why. The STM32 is the standard for heavy automation, motor control, and robotics. When a machine operates around the clock, timing deviations cause physical damage. Here is the STM32's block diagram. It achieves reliability by separating fast and slow operations across parallel pathways, the advanced high-performance and peripheral buses. Notice the DMA controller. It writes sensor data straight to memory. The CPU never wakes up, guaranteeing deterministic real-time performance. Achieving this performance requires a strict software investment. Your firmware team has to master a steep learning curve, making precise choices between the high-level hardware abstraction layer and bare-metal low-layer drivers. The hardware demands are equally strict. To keep that complex internal silicon stable, the schematic requires meticulous multi-layer ground routing, precise decoupling capacitor placement, and a robust power architecture to prevent sudden brownout resets from factory floor noise. You choose the STM32 when timing and reliability absolutely cannot fail, accepting rigorous upfront engineering demands. If your product runs on a coin cell battery, the Nordic NRF series is the definitive choice, engineered for ultra-low power wearables and medical sensors. This chart compares standby power consumption. A standard MCU idles in the milliamp range, but the Nordic chip drops into deep sleep states, drawing mere microamps. To transmit Bluetooth data, the radio fires a microscopic burst, instantly returning to near zero. The energy budget remains tiny. The cost of this efficiency shows up in 2 places: a higher unit price on the bill of materials and the requirement to write code within highly complex event-driven Bluetooth software stacks like Zephyr RTOS. Nordic dominates the battery life war. It allows for sleek, long-lasting physical designs, provided your team has the firmware expertise to navigate its software ecosystem. The ESP32 is built for instant cloud connectivity and heavy data streaming. It powers millions of smart home appliances and IoT gateways. It packages dual-core processing, built-in Wi-Fi, and Bluetooth into a single module at a price point that undercuts almost everything else on the market. This bar chart of peak current draw reveals the primary trade-off. The ESP32 requires massive amounts of energy to sustain its wireless connections, completely towering over the consumption of STM32 and Nordic architectures. There are also hidden hardware risks. If you design a custom PCB without using pre-certified modules, routing that much RF power requires highly specialized electromagnetic interference tuning, or the chip will deafen its own antennas. The ESP32 provides massive computational strength and immediate cloud access on a tight budget. It is an excellent choice, as long as your product is permanently plugged into a wall. The RP2040 offers a different approach to peripheral control compared to the established ARM-based families. Look at its programmable I/O, or PIO blocks. These independent hardware state machines emulate almost any interface, like VGA or custom sensors, without tying up the main processors. However, lacking built-in flash memory, your schematic requires an external memory chip, complicating the PCB layout. It also lacks the decades of deep automotive and life-critical industrial certifications that legacy families like the STM32 carry. If you need to shovel massive amounts of custom data on a strict budget, the RP2040 is brilliant. Just keep it out of environments that require hardened, certified reliability. Understanding internal silicon is only the first step. Translating knowledge into a mass production decision requires testing hardware constraints against your product requirements. This decision tree maps how architects filter constraints. Every choice cascades into physical schematic requirements. Take an industrial motor controller. The constraints are strict timing and high reliability, with no wireless communication. The tree naturally resolves to the STM32. Selecting this specific node dictates the rest of your design. You are now required to design a strict power architecture using low dropout regulators and bulk capacitance to prevent resets during motor spikes. Now consider a medical wearable. The bottleneck is battery life and Bluetooth. This path locks into the Nordic NRF. This choice shifts the engineering burden. Your hardware team must design a flawless, leak-free power tree, and the software team adapts to a complex real-time operating system. For a smart home wall plug, priorities change. Mains powered, needs Wi-Fi, and a razor-thin profit margin. The ESP32 is the resolution. Because power consumption is irrelevant, the hardware design is simplified. Engineering focus shifts entirely to firmware security and managing over-the-air updates. Finally, designing a custom LED matrix controller requiring high-speed data pushing on a strict budget, you arrive at the RP2040. These four paths demonstrate that every choice involves a specific trade-off. No single microcontroller ever fits every single product requirement. Every feature built into a piece of silicon carries a cost. Hardware architects evaluate compute power against bill of materials cost, component availability, and the time it takes to write the firmware. Professional engineering comes down to recognizing when a project's constraints have outgrown a familiar architecture and having the discipline to switch to the silicon